This is an abridged version of the presentation on uphill diffusion that can be viewed on my YouTube channel. Here is a picture taken in the Antarctica showing fortresses of ice containing nearly pure water happily coexisting with seawater containing salt. Apparently, the Fick's law of diffusion does not seem to apply here because there is no diffusion of sodium chloride into the ice fortresses. Let's examine the reasons why. This graph plots the molar Gibbs free energy of ice and seawater as a function of mole fraction of sodium chloride. The phase equilibrium between the ice fortresses and seawater is described by the common tangent. And this common tangent intersects the y-axis at this point at which the chemical potential of water in the seawater is equal to the chemical potential of water in ice. At the other end, the common tangent intersects the y-axis at the chemical potential of sodium chloride that has the same value in seawater as in ice. So we note that at thermodynamic equilibrium, the seawater contains a significantly larger amount of sodium chloride than the ice fortresses. The reason there is no diffusion of sodium chloride into the ice fortress is because the system is in thermodynamic equilibrium. The inescapable conclusion to be drawn from this example is that species diffusion is driven by the gradient of the chemical potential rather than the gradient of the mole fraction as is assumed in the Fick's law of diffusion. Having established that chemical potential gradients are the proper driving forces for diffusion, let us examine the possibility of uphill diffusion in binary mixtures. As an example, let's consider mixtures of iron-chromium alloys. Applying the Gibbs-Duhem constraint, we note that there is only one chemical potential gradient that is independent, and we can write the chemical potential gradient in terms of the gradients in the atom fraction by defining a factor gamma, which is a thermodynamic correction factor defined by this expression. Gamma can be calculated from information on the non-ideal solution thermodynamics. For all temperatures above 1100 degree Kelvin, the iron-chromium mixture is homogeneous, and when this mixture is subject to perturbations, the diffusion will occur to even out these fluctuations and result in uniform compositions. However, as the temperature is reduced below 1100 degree Kelvin, there's a region where phase splitting occurs. The green line shows the binodal curve and the red line shows the spinodal curve. Along the spinodal curve, the thermodynamic correction factor is 0 and gamma is less than 0 in this region. What we note is that if gamma is less than 0, then the activity gradient is opposite in sign to the gradient in the atom fraction. To illustrate this, let us consider the calculations of the activities at a temperature of 800 Kelvin. The activity of iron as a function of atom fraction of iron is plotted by the red curve. And in this unstable region, we note that as we increase the atom fraction of iron, X1, the activity of iron decreases. So the gradient of activity is opposite in sign to the gradient of the atom fraction of iron. The same is true for the activity of chromium. In this region, the gradient in the activity of chromium is opposite in sign to the gradient in the mole fraction or atom fraction of chromium. We would therefore expect in this region diffusion to be down the activity gradient but up the gradient in the atom fraction. Let us illustrate that by taking a 50-50 mixture and subjecting it to a perturbation. And we see in the simulation that segregation occurs with islands of chromium atoms surrounded by a matrix which is rich in iron. Let's have a look at the classic experiments reported by Lawrence Stamper Darkin in his classic paper published in 1949. Two bars of steel of different compositions are brought into contact with each other. The carbon content of the two bars are practically identical. However, the left bar contains a significantly higher percentage of silicon, the remainder being iron. These two bars of steel are placed in a furnace at a temperature of 1323 degree Kelvin for 13 days. At the end of that period, the bars are quenched and the weight percent carbon determined as a distance from the weld interface. The data are plotted by the red circles in this graph. We note that there is a decline in the weight percent of carbon as the interface is approached from the left bar, and then the weight percent of carbon increases to reach a maximum in the right-hand compartment, and then finally decreases in value to the initial value of 0.45%. In this region close to the weld interface, we have diffusion of carbon up the concentration uphill, where the concentrations are expressed in weight percent carbon. Now, the higher weight percent of carbon near the surface of the right bar imparts a higher hardness to the bar, whereas the bulk is tougher. And this method of carburization of steel exploits the phenomena of uphill diffusion. Let us examine the fundamental reasons for the uphill diffusion of carbon and steel. For the ternary mixture of carbon, silicon, and iron, there are two independent chemical potential gradients that can be related to the gradients in the weight percent of carbon and the weight percent of silicon by the thermodynamic correction factors gamma that can be calculated using a model such as the regular solution theory, and the addition of silicon for a given weight percent carbon increases its activity, and therefore these factors, the gamma 12 and gamma 21, are non-zero and have significant magnitudes. Put another way, the activity gradient of carbon is related not only to the weight percent gradient of carbon, but also to the weight percent gradient of silicon. Using information on the thermodynamic correction factors determined from the regular solution theory, the experimental data measured by Darkin can be replotted as shown in this graph, in which the activity is plotted as a distance from the weld interface. We note that the experimental data shows that the diffusion goes monotonically down the activity hill of carbon. The message to be drawn from these set of experiments is that the thermodynamically correct driving force for diffusion is the gradient in the chemical potential, or equivalently the gradient in the activity of any component. Having established that chemical potential gradients are the proper driving forces for diffusion, let us see how best to set up the formulation describing the diffusion fluxes in terms of the chemical potential gradients. The most convenient formulation is to adopt the approach developed originally by James Clerk Maxwell and Maxwell-Stefan to describe diffusion in mixtures of ideal gases. Let us therefore start the analysis by considering a mixture of three components. The force acting per mole of species 1 is the negative of the chemical potential gradient at constant temperature and pressure. This is balanced by the friction component 1 experiences in undergoing a relative motion with respect to species 2, and the friction it experiences in undergoing relative motion with respect to species 3. Similarly, we can write an expression for the force acting per mole of species 2 and relate it to the friction between 2 and 1 and between 2 and 3. We define the Maxwell-Stefan diffusivities in this manner, and the Maxwell-Stefan diffusivities are differentiated from the Fick diffusivities by using the symbol D with a line through it. On the basis of this formulation, it is evident that the physical significance of the Maxwell-Stefan diffusivities is that it represents an inverse drag coefficient. Using RT in the numerator ensures that the units of the Maxwell-Stefan diffusivities are square meters per second, as is commonly used to describe diffusion phenomena. We need the multipliers x2 and x3, which represent the mole fractions of components 2 and 3, because the friction between component 1 and 2 should depend on the relative amounts of components 1 and 2 in the mixture, and that is taken care of by these multipliers involving the mole fractions. We need consider only two of these equations because of the Gibbs-Dion constraint on the chemical potential gradients. Using two-dimensional matrix notation, we can shoehorn the set of two Maxwell-Stefan equations shown on the previous slide into a Fickian form. A column vector of molar diffusion fluxes, defined here, is related to a column vector of mole fraction gradients via a square matrix of Fickian diffusivities. Vm is the molar volume of the mixture. Using a straightforward algebra, we can derive an expression to explicitly calculate the elements d11, d12, d21, and d22 in terms of the Maxwell-Stefan diffusivities of the three binary pairs d12, d13, and d23. This expression is given here. It's noteworthy that the diagonal elements are some kind of average of the Maxwell-Stefan diffusivities, whereas the off-diagonal elements are proportional to differences in the pair Maxwell-Stefan diffusivities. As an example, let us consider a ternary mixture consisting of hydrogen, component 1, nitrogen, component 2, carbon dioxide, component 3, and calculate the diffusivities at a temperature of 308 Kelvin at the mole fraction x1 equals 0.25, x2 equals 0.5, and x3 equals 0.25. From the kinetic gas theory, the Maxwell-Stefan pair diffusivities can be calculated as 8.33 10⁻⁵ for the 1,2 pair, which is hydrogen-nitrogen. This is for the hydrogen-carbon dioxide pair, and this is for the nitrogen-carbon dioxide pair. We note that these diffusivity values are significantly higher than the diffusivity for the nitrogen-CO2 pair because hydrogen is the smallest of the three guest molecules. Using this expression, we can calculate the matrix of the Fick diffusivities as follows. It's interesting to note that the cross coefficient here, D21, is minus 3.83, whereas the diagonal element here, D22, is 2.15. This implies that if we have a situation in which the gradient of the mole fraction of component 2 is 0, which is component 2 is nitrogen, then the flux of nitrogen J2 will not be 0 because it will be dictated by D21 times dx1 dz, and D21 is large and negative, and therefore we should experience uphill diffusion for conditions in which we can ensure that dx2 by dz is 0. Let us see if this expectation is borne out in experiments. Duncan and Tour in 1962 published a set of experiments in a two-bulb diffusion apparatus with the ternary mixture of hydrogen, nitrogen, and carbon dioxide. The initial compositions of this mixture in bulb A is shown by this point here, and the initial composition in bulb B is shown by this point here in the ternary composition space. At time t equal to 0, the capillary tube connecting the two bulbs is opened and the interdiffusion is allowed to take place. the composition trajectories followed in bulb A is indicated by the red circles, and in bulb B by the green squares. It's interesting to note that the equilibration trajectory does not follow a straight line path, rather it has a serpentine character. In this graph, the set of data on the mole fractions in bulb A and bulb B are plotted as a function of time. The equilibration of hydrogen and carbon dioxide follows the exponential trajectories one would normally expect for a diffusion governed equilibration process. Nitrogen, on the other hand, has a different character. The initial composition of nitrogen in both bulbs is exactly the same. In other words, there is no driving force for nitrogen, and yet this does not prevent nitrogen from diffusing. For example, in bulb A, the composition decreases from the initial value of 0.5 and continues to decrease till this point is reached, and then it increases in value. The composition in bulb B, on the other hand, increases from 0.5, reaches a maximum, and then decreases eventually to equilibrate at very long times. During the interval 0 to 6 hours, nitrogen experiences uphill diffusion. As was expected on the basis of the calculations we presented in the foregoing slide for the Fick diffusivity matrix that was evaluated at the average between this composition and this composition. So the uphill diffusion is a direct consequence of the friction between components 2 and 3. Even though the composition gradient of nitrogen is 0, due to the large drag between nitrogen and carbon dioxide, nitrogen is dragged from bulb A to bulb B. From bulb A to bulb B, as a consequence, the mole fraction of nitrogen decreases in bulb A, and concomitantly the mole fraction of nitrogen in bulb B increases. Therefore, we draw the conclusion that even in a ternary gas mixture, it is possible to experience uphill diffusion due to differences in the drags coefficients of the 3 binary pairs. Another conclusion to be drawn, as will be confirmed in several examples to be presented later in this presentation, is that a consequence of uphill diffusion is that the equilibration trajectory that is followed in composition space has a serpentine character. A physical appreciation of uphill diffusion in ideal gas mixtures can be obtained by observing the countercurrent influx and efflux of passengers in a Mumbai local train. A passenger who just wants to remain within the train may get dragged out of it, reluctantly I might add, by the strong drag experienced with a fellow passenger who is leaving the train. The Maxwell-Stefan approach for diffusion in ideal gas mixtures can be extended to non-ideal systems by introducing thermodynamic correction factors that involve the activity coefficients. The thermodynamic factors can be calculated for liquid mixtures using, say, the NRTL and Uniquac equation, for supercritical gases using the Peng-Robinson equation of state, for polymer solutions using the Fleury-Huggins model, for metal alloys using the Calfad model. For a ternary mixture, the departures from ideality is described by a matrix of thermodynamics correction factors whose off-diagonal elements are generally large and non-zero. The off-diagonal elements of the thermodynamic factor matrix contributes to a large extent to the off-diagonal elements of the Fick diffusivity matrix, and these off-diagonal elements lead to the phenomena of uphill diffusion, as we shall see in the next slide. Let us consider a set of experiments reported by Varshney and Cooper for diffusion in a ternary mixture consisting of metal oxides of potassium, strontium, and silicon. Two slabs of two different compositions are placed in contact with each other and raised to a temperature of 1071 Kelvin and held at that temperature for 4.55 hours. At the end of that time period, the system is quenched and the compositions in either compartment determine the weight percentage of potassium oxide is indicated by the green squares here, and the red circles show the compositions for strontium oxide at either side of the interface between the two slabs. We note that strontium oxide, component 2 in our ternary mixture, experiences uphill diffusion in this region, and when plotted in two-dimensional composition space, we note that the equilibration trajectory exhibits a serpentine character. The continuous blue lines are the equilibration trajectories calculated with the value of the Fick diffusivity matrix given here. We note that the off-diagonal element D21 of the Fick diffusivity matrix is significantly larger than the diagonal element D22 and is also negative in sign. Therefore, component 2, which is strontium oxide, is strongly coupled to the composition gradient of component 1, which is potassium oxide. And this coupling causes uphill diffusion. If the coupling effects were to be ignored and the equilibration trajectory calculated using a simple model in which the flux of each component is considered to be proportional to its own composition gradient, then we obtained a straight line shown here. And no uphill diffusion will be predicted. Ouzo is an aniseed-based drink consisting of 45% ethanol, 55% water, and 0.1% transanethol. This is the phase diagram for this ternary mixture. There's a region in which we have phase splitting. When you add ouzo to water, it turns cloudy, indicating the entry into the metastable region. Let's have a look at the experiment. Clearly, the entry into this metastable region must imply that the trajectory followed is serpentine in character and not straight. If a straight line trajectory were to be followed, then no entry into the metastable region is possible. Therefore, it's to be concluded that the actual path is caused due to strong non-idealities in the ternary diffusion process. Now, the Ouzo effect can be exploited to produce nanospheres, and this is very energy efficient because no expenditure of energy is required, because this formation of metastable suspensions is spontaneous. For processes such as reverse osmosis, ion exchange, electrodialysis, additional driving forces come into play. These driving forces could be due to pressure gradients and electrostatic potential gradients. For transport of ionic species, Z1 would be the charge number and F the Faraday constant. And in addition to the Gibbs-Duhem constraint on the chemical potential gradients, we need to invoke the electro neutrality constraint shown by this equation. The interactions of species 1, say with the walls of the membrane, can be accounted for by introducing an additional frictional term in which the wall is treated as a pseudo-species in the mixture. And this term, for example, could be used to describe water transport across a reverse osmosis membrane. Let's examine the phenomenon of osmosis. We take a vessel divided into two compartments by a membrane. The right compartment contains 100% pure water, and the left compartment contains salt water containing 2% salt. The membrane consists of a polyamide thin film with a pore size of about half a nanometer. The membrane allows water transport but prevents the transport of salt across the membrane. Initially, there's a driving force for water transport from the right compartment to the left compartment due to the differences in the composition of water. The diffusion will continue to take place till osmotic equilibrium is reached, at which the sum of the chemical potential gradients and the pressure gradient term is zero. For the chosen set of conditions, the osmotic pressure can be calculated to be 2.8 megapascals. By applying pressures exceeding 2.8 megapascals to salt water contained in the left compartment, water can be made to diffuse uphill from the left compartment to the right compartment. The Maxwell-Stefan equations describing water transport is shown here, where the left member quantifies the force acting per mole of water, and the right member of the Maxwell-Stefan equation represents the friction water experiences in undergoing relative motion with respect to the membrane. dWm represents the Maxwell-Stefan diffusivity for water membrane transport. There's a wide variety of applications for reverse osmosis in several different contexts. In Bengaluru, RO water is used in the vending machines to serve pani puri to enthusiastic customers, as shown here in this picture. The separation of the isotopes of uranium, U-235 and U-238, by applying centrifugal force is another example of the exploitation of uphill diffusion. In practice, rotational speeds of 40,000 RPM are applied to create a pressure gradient that is described by this equation. The application of pressure gradient tends to have the effect of moving the heavier isotope towards the periphery. And if we start with a uniform composition mixture, the compositions at the periphery would be richer in the heavier isotope, because the heavier isotope experiences a larger effect of the centrifugal force. Now, due to the large rotational speeds used, the dimensions of the centrifuge need to be restricted, and typically the centrifuge diameters are less than about 10 centimeters, and to obtain the high capacities required in nuclear plants, a few million centrifuges are required, and for purity considerations, these centrifuges are arranged in cascades of centrifuges placed in parallel and in series. Yang and Pintaro report a set of experiments for transient diffusion of ions across a cation exchange membrane. The system consists of two compartments, a salt compartment on the left side and an acid compartment on the right side of the Nafion cation exchange membrane. The salt compartment contains a mixture of 0.125 molar sodium sulfate solution and a 0.0054 molar cesium sulfate solution. The acid compartment contains initially 0.125 molar solutions of sulfuric acid. The cation exchange membrane prevents the intermembrane transport of the sulfate anions and allows only the passage of sodium, cesium, and hydrogen ions. The experimental data for the transient uptake of hydrogen ion in the left compartment is shown by the red circles here, and the transient influx of sodium and cesium in the right compartment is shown by the green squares and the blue triangles. It is to be noted that the concentration of cesium in the right compartment exhibits a significant overshoot before it approaches its equilibrium value in the right compartment. The explanation for the uphill transport of cesium and the attainment of supra-equilibrium concentrations of cesium is explained simply in terms of the electroneutrality constraint that must be obeyed. Now, hydrogen ion has a diffusivity that is a factor 5 higher than the diffusivities of either sodium or cesium, and therefore the diffusion of hydrogen ion takes place very quickly, and it enters the salt compartment far more quickly than the egress of sodium cations and cesium cations. The fast entry of hydrogen ions into the left compartment causes an excess of positive charge, and that positive charge creates an electrostatic leash that enhances the transport of cesium from the left compartment to the right compartment in order to maintain electroneutrality in this compartment. So, uphill diffusion in this case is a consequence of the requirement of electroneutrality. The major takeaways from this presentation on uphill diffusion are summarized here. The proper driving forces for molecular diffusion is the chemical potential gradient. For processes such as reverse osmosis and ion exchange, the driving forces must be augmented to include pressure gradients and electrostatic potential gradients. The most convenient formulation for diffusion is the Maxwell-Stefan formulation, in which the driving force acting on a species is balanced by friction which the species experiences with partner species and with the pore wall of membranes. In most of the examples we have encountered, uphill diffusion is caused by thermodynamic coupling effects and by electroneutrality constraints. The signatures of uphill diffusion are transient overshoots and serpentine equilibration trajectories in composition space. Put more simply, the uphill diffusion follows the scenic route that may open new vistas. In the socio-economic sphere, the phenomena of uphill diffusion results in ethnic enclaves. As evidence, have a look at the district called Little Italy in New York, the Chinatown in San Francisco, Southall in London. Note the Gurmukhi script here. In the area of Matunga in Mumbai, there's a high proportion of people who originated from the south of India, and there is a preponderance of Udupi restaurants in Matunga.